ಮನೆಲ್ಲ ಕೂಡ ತರದ್ದು
Yeah, good evening to one and all present here. Welcome you all to the third day of our FDP on convergence of quantum computing and Gen AI for frontier scale revolution. And today we have a session which is on quantum programming. Here's a short introduction. He has been a quantum researcher, trainer, as well as IBM certified Qiskit developer. So apart from this, he has worked in versatile projects with different types of clients. Also, he's having work experience in different environments like IBM mainframe and databases like Oracle 10G. And he started learning the programming languages from COBOL. And he's worked in various phases of our SDLC, specifically to be notable in developing and testing. He has he has a passion for learning different types of stuffs, and now he has better passion in this particular quantum computing. So over to you, sir.
Okay, thank you, madam. Good evening to all of you. Actually, I started my career in quantum since in 2017. From there, I have been sailing in this new field, emerging technology. Okay, without any delay, I will dive into the current topic, which is how to program the quantum computers, especially IBM quantum hardware, using Qiskit one. Okay. Okay, is my screen visible, madam? PPT is
yes,
visible,
sir, visible,
madam?
visible. Yeah, visible.
Okay,
sir.
okay.
Ah.
This is the third day I'm taking care. I'm delivering this programming on IBM quantum hardware, and on day one, professor from NIT Trichy has introduced about the concepts and all the quantum mechanical principles based on which this quantum computing has emerging, and still it is evolving. Okay, and he also introduced, I think he also introduced the architecture of this quantum computer. And in day 2, which was delivered by Karthik Ganeshan, he has introduced you to the advanced concepts like quantum algorithms and quantum inspired algorithms, as well as HPC's HPC computers, high performance computing. Today, after having all those basics, let us dive into the concept how to program this quantum programming. Okay. Now this seems I'm revisiting this one. Here, how data will flow from, you will be having the data center, and the middle chamber is the quantum chamber. Inside this one is the quantum processor, where all our processing of data will happen, and data will flow from the data center. From data center, clients will initiate the data transfer from data center Here, which will in this client, which is our normal laptop or computer, will convert all the data into the binary bits that will be flown into this top a component called analog electronic converters, where our binary data will be converted into the quantum state that will be sent inside the processor. Here, actually, all the executions of or processing of data, that means our quantum state will happen here. And after that processing, the output will be sent back to the client. Here again, here at analog electronic converters, these quantum states or whatever the data which will be the output from the processing QPU will be again converted back into the binary data, and it will be sent to the user. This is how it will happen. And this is the data flow. And here only hardware perspective, this components that will be taken care of the hardware personals. So I'm not going deep dive into here. Now, these are the principles which you, for the last 2 days, which you are being introduced, and for completeness, I am again revisiting this superposition principle, entangle principle, and interference. Again, superposition principle, as you know, as you might have known, that the quantum state system at one time. This, because of this superposition principles, parallel processing of data will happen in quantum computer. And this entanglement is generally used for to teleport your quantum states from one place to another one. Recently, in the last May, Cisco has delivered one entanglement chip, which is used. It is a protocol they will be using in their network applications. Still, they are. Then after that, this interference is a concept which is exhibited by the two types of interference is there: constructive interference and destructive interference. This concept is used in the machine learning and optimization problems. Then again, same thing. Here qubits, and okay, let us go on to. Now coming to the quantum programming, actually there are several dozens, actually 10 to 12 frameworks or packages are available in the market for programming the quantum computers, but the one that was given by the IBM is the front runner in this race. And let us see what are the few of them, what are the available, most available or mostly used patterns, not patterns, frameworks. These are the first one is the Qiskit. It was developed by IBM, and Python is using. To write the programs, we'll use the Python, and it provides the strong ecosystem for quantum hardware and simulators. Apart from this, Qiskit now Qiskit in the back end, Qiskit is being developed by Rust programming language, which provides at the circuit level. Even beyond the circuit level, there is one more level of programming called the pulse level programming. That pulse level programs are being developed in, or APIs are being developed in the Rust programming language. That we will not discuss in this one, and it is also not that goes to the hardware persons for Rust programming, pulse programming. And the Google's quantum programming framework is the Kirk. Again, here it is being developed by using the Python. Recently, Sycamore is the quantum processor that has been delivered to the market by the Google. And the third one is Q-Sharp. This is being developed by the Microsoft, and it is not using Python. This is being developed by C# language, and the latest QPU developed by this Microsoft is Mazurana 1. Then there is Bracket, which is the product of Amazon. Again, here Python is being used for developing this Bracket SDK. Then the beauty of this Bracket is that from using Bracket, you can connect, you can submit your quantum programs to the third-party hardwares. That means you can write your programs in Bracket, and you can run those programs using APIs that has been submitted by the vendor. So that means, suppose if you want to execute your programs, quantum programs that was been developed in Bracket in IBM quantum hardwares, you can do that one using the Rust APIs. Rust APIs is there. And the last one is the PennyLang. This is being developed by the Jandu company. Again, here Python is using. This PennyLang is mainly used for optimization problems, especially in quantum machine learning and LLM also. Now here we are going to deal with Qiskit only. And why Qiskit? Qiskit is an open source program, open source SDK that is being developed and maintained by IBM. And IBM is providing some runtime environment, which we will discuss in later slides. That is the core component to program a quantum computer using a Qiskit. And afterwards, apart from this, the Qiskit is organized in such a way that it is circuits. It was being organized in different components, which is easy to identify which model to be used for which purpose. There are few the few features that has been included in the Qiskit. The list is exhaustive. I am showing only few things. Here, Qiskit includes circuit building tools, which we will see now, and using Qiskit, and the circuit library is one more module that is being provided here. Here in circuit library, all the well-tested. Madam, there is some disturbance, madam.
Yes, sir. 1 minute.
Hello.
Sir. Yes, sir. Yes, sir. Participant, please unmute yourself. Sir, please unmute yourself, sir. Jay Kumar, sir, can you hear me? Jay Kumar, sir, unmute yourself, sir. Sir, you have been muted. Please unmute.
Okay. Now is it okay, madam? Madam, is it okay?
Yes, sir.
Yes, sir. Yes, sir.
Okay.
Yeah, fine, sir.
1 minute, madam. Circuit, this Qiskit is organized in such a way that we can identify which module we will use for which purposes. For example, circuit library is the one where all the well-tested circuits like Grover's diffusion operator, these are all advanced source QFT, and that we will see here. I will show you the gate also. Like that, well-tested circuits as well as gates will be housed in the circuit library. Again, suppose if you want, the quantum info library is the place where you will get from which, using the modules or methods, functions from the quantum info library module, you can retrieve the characteristics of the quantum circuit. Then runtime service is the core part of the entire program development using Qiskit. Runtime services, it acts as an interface between the programmer and the quantum hardware. And that also we will see. Transpiler is the place where you will convert your circuits into the circuits that are compatible to the IBM quantum hardware. We'll go deep into this one also. And primitives is also one part where we will use for executing the circuits. All these are all organized in a well-fashioned way so that it is very big, it is very easy. Previously, now the Qiskit version is 2.0, which was released in the July 1st onwards. We have been using the Qiskit 2.0 version, but at the advent of this Qiskit, this entire package is not structured or organized in so that to learn or it was, I faced so much of problems. Now it is good. This is the runtime environment. Actually, it is a cloud-based environment, and it is not an open source. It is developed. It is entirely a IBM's product. It is developed and maintained by IBM, but it is not an open source program, open source one. Okay. As I just a couple of minutes before, I told that IBM runtime is an interface between the user and the quantum hardware. I will show you the how to do that one. Let me. Now, just like in Qiskit, in normal computing, suppose if you want to develop an application or if you want to add an functionality to an existing application, there is a process called SDLC, Software Development Life Cycle, through which we will every step will go some iterations till the particular consensus has been met between the customer and the vendors. Then only they will go for that means brainstorming will happen. Similarly, here also Qiskit we are using the development workflow is defined in terms of the Qiskit patterns. Why? Because why we are using this Qiskit patterns means for best practices or guidelines how to, it provides you the guidelines for developing your quantum computing programs. And it maintain, but then the other purpose is for readability, scalability, and reliability are the one of few characteristics that are well defined in this documentation of Qiskit patterns. Now, before going into this actual workflow, let me introduce the, actually yesterday KG sir, Karthik Ganeshan has tried to show this runtime services or cloud-based thing. I will show you now. Because of it, I will show you now. This is the one. Screen is visible, madam. Hello.
Yes, sir.
Yes, sir. Yes, sir.
Yes, sir.
Sign into
Visible.
IBM Quantum Platform. Screen is visible, right?
Yes, sir. Visible.
Okay, madam. Okay, thank you. This is the quantum user interface, madam. This is the place where you are having. And here, if you see here, yesterday itself, this is the API. Okay, at this time of setup, you will do this one. If you click on the left side, you will see the home, instances, workloads, compute resources, analytics, access management, document learning, right? Here, if you see the compute resources, it will show you the available IBM target hardware, quantum hardware. The thing, if you see in the left side, you will find the QPU name. IBM Pittsburgh, IBM Kingston, like that. There are six IBM quantum hardwares are available, out of which 2 are available for open users like us, and remaining the 4 which has been prefixed with lock icon, those are only available to the premium subscribers. Okay, and within this one you will be given 10 minutes of QPU time, where you can see your say here. If you see here under the, if you go to the left and click on the instances, you will see this one here, total available to the time, that is 10 minutes total available, and I have used almost 1 minute 16 seconds. So still there are, you will be, I was left with for usage of 8 minutes 44 seconds. This is the one. Now, workloads, what are the jobs that have been submitted, you can see here. These are all the job IDs. Anyhow, I will show you after one. I will show you running 2 jobs in this session. That, and how to retrieve those details also I will show you. These are the, from here you can take your job ID, job details, entire thing you will be seen here. Suppose again, if you go into the compute resources, if you see here, status is there. No? For every 24 hours, IBM will recalibrate every day of these quantum computers. While doing recalibration, the status will be offline, that so that it is not available to for submission of jobs. And if you see here, how many jobs are pending in the, for the, with respect to each IBM quantum hardware. These are the things. Apart from this, the number of qubits that has been supported by that particular IBM hardware will be listed here in the qubit column. So far, the real IBM quantum computer has a maximum of 156 qubits supported by the target IBM. That means real quantum computers so far now it has been, IBM's can accommodate up to 156 qubits. Okay, this is the one. Okay, now let me get back to the now Qiskit development. After this one, before Qiskit 1.0, there are 4 types of the Qiskit patterns. That here are those 4 things: circuit execution pattern, variational pattern, quantum kernel pattern, sampler and estimator pattern. The first one has been clubbed into the, that means circuit execution pattern was clubbed into the sampler and estimator pattern. And the third one, which is called quantum kernel pattern, has been deprecated now. So totally we are having only 2 execution patterns, 2 patterns only. That is sampler and execution estimator pattern and variational pattern. Actually, Qiskit, the circuits or the programs are of 2 types in Qiskit quantum programs. One is the standalone program and the second one is the hybrid one. In the standalone program, it will consist, the statements will consist of only the statements related to the Qiskit. But in the hybrid one, you will be having some apart from the Qiskit patterns. These hybrid ones are used for, especially useful in QML one. If you want to run, suppose if you want to do all the optimization in QML, what it will do in quantum machine learning, execution part will happen in the quantum computer, and all the optimization parameters or optimization will happen in the normal computer, in the conventional computers. This type of circuits are called the hybrid quantum programs. Now, even whatever the Qiskit pattern you will use, it has 4 steps, and these 4 steps we are going to see in detail. These 4 steps are called the, first one is called the mapping, second one is optimization, or some literature they are giving transpilation. Both are same only. And third one is the execution, and last one is the post-process results, where you will see your results and visualizations will happen in the 4th step. Here, if you see here in the screen, next we'll see. Okay, the first step is the mapping problem. Actually, mapping problem is there will be some domain-specific problems is there, such as the in financial modeling, portfolio things, suppose portfolio optimization. Then if you are good in futures and options derivatives, their options are very being used for this options pricings can be done using this quantum circuit, so that the traders can earn more money. I will tell you the later which one is using that options pricing, which company is using. Here there will be a domain specific problem. That domain specific problem is converted into the quantum circuits. That means you are mapping your problem to the quantum circuits and operators. This quantum circuit, the user can have, based on the complexity of the problem, he can choose how many qubits or gates, whatever may be the things. He may choose as many qubits or as many operators. Instructions also. Instructions means classical feed forward. Suppose in a normal computer, in a normal programming language such as Python or in Java, there will be the if control flow statements, means if statements, for loop, iteration over some iterations. All those will be, you can include in your circuits. That one is called the abstract circuit. The circuit that is being created in this mapping step is called the abstract circuit or logical circuit. Okay, here all the qubits that are being used are called logical qubits, not the physical qubits. Physical qubits will be there in the IBM quantum hardware. This is the generally the Qiskits can be categorized, circuits in the Qiskit can be categorized into two types called the abstract circuit, and the second one is the physical circuit. This in the mapping stage you will get the abstract circuit, and in the next step you will get the physical circuit. The technical term for physical circuit is called ISA circuit, that we will see how it will be the structure, how it is, we will see. And by executing two programs, I will show you the abstract circuit. And these are the various components. What can you include? You can define the problem in terms of virtual qubits. You can add arbitrary level of operations. Means, suppose if you have 100 qubits, means you can add multi-control gates for single qubit gates, whatever may be. It depends upon the problem definition, and which operators that is being used will be given by the physicists and mathematicians. Also, if there, as I told you that previously, that there will be well-tested programs and gates that are being housed in the circuit library. You can use those gates and circuits also as an submodule in your abstract circuit. Just like if within the program you will define the subroutines, right? So functions like that you can do here also. Now we are going to enter into the transpilation. Before going into this one, let me show the abstract circuit. See, before going into the abstract circuit, I will show you how to retrieve the properties of that quantum hardware. This one, the first one, madam, this my Jupyter notebook is visible, madam. Hello.
Yes,
My Jupyter notebook is visible.
Yes, sir. Yes, sir.
Okay, madam. This is the primer one. Here, all your, I told you, no, this Qiskit runtime service is the core part of this IBM quantum programming. So this is the place in the IBM quantum. Before submitting the programs, you need to be a reliable user. How the will know? Because of this entire securities API, based on this API application programming interface gate, this is done. It establishes the reliability of the end user. In where you will find this one means I cannot show because it will disappear. It will disappear as soon as you create the instances. It will be disappear. Only the thing that is visible is the CRN. CRN means compute resource name. This one will be taken care by the cloud provider, which is IBM, and the administrators, cloud management people will take care of these CRN things. Actually, here you cannot create. Here, if you see here, create instance in the right side here. This is the place you can create your instances. Once if you create this one, after giving the instance name, everything, you will be getting the API key will be created. That one you have to copy or safeguard your API somewhere within the local computer. It should not be revealed to the outsiders. This is my API, and this is the CRN number. From this, I am going to save my credentials. I'm going to run this one. Once it run. Once I run, I am going to see whether the connection has been established or not. Those how we looking all these things we there, no? Verify. That will establish your connectivity to the runtime services as well as your quantum hardware. Once I have connected, I'm going to retrieve 1 minute. I'm going to show one more thing. Okay. I'm going to retrieve using this statement. Service.backend will give you all the backends that you are authorized to, you have access to. That means you can submit your jobs late. Backend equal to if I run this one, it will show you some syntax error is there. 1 minute. See, these are the two IBM hardware that I am authorized to submit my jobs. And where you can find here in the user interface, compute resources, here you can find IBM Torino and IBM Brisbane. Now, suppose I want to retrieve the backend properties, means this is how I'm going to run, so that only the physical characteristics I am going to retrieve. So, say how this one. This is the Brisbane characteristic. Name is IBM Brisbane. Description is not available. Which version it is, and the processor family is Eagle, and revision. Revision is 3rd. Number of qubits, that is this one. All this data. And this one, coupling map is very important, that we will see in the later part. And see, if you see here, basis gates are there. How many gates? Totally there are 5 basis gates. But if you see here, operations separated, these are all apart from these basis gates. It has included some other instructions such as measure, reset, and delay. These are the instructions apart from the basis gates. These are also supported. Similarly, for the second one, IBM Torino, the same thing is there. In this way, you can retrieve the physical characteristics of this IBM quantum hardware. Generally, the characteristics of classified into 2 types. One is the physical characteristics. Second one is the dynamic characteristics. That dynamic characteristics will keep on changes, but physical characteristics will remain as it is. Why they will keeps on changing means because of the calibration that is being done for every 24 hours. Madam, up to here, any doubts, madam? Before going further, please ask me.
Yes, so participants, if you have any doubts, you can ask.
Okay, madam, I'm going forward.
Yes. Yes, sir.
Now we are going to the transpilation step. That is the second step in the Qiskit pattern. Actually, what is meant by transpilation generally in computer terminology? The transpilation, suppose if you have one language that is being written in the Java, and I want to convert that language into some other high-level language, say some C or C++ or Python. Process, you can convert this one. There are so many interpreters are available using which you can convert one high-level language program into the another high-level program. That is the generic definition for transpilation. Similarly, here we want to convert our user-defined abstract circuit into the hardware compliant circuit. Using transpilation, we can do it. Why it is needed? Because if you see in the just now I have shown you that the basis gate sets for IBM Torino computer hardware and IBM Brisbane hardware, both are having the universal set of gates. These universal set of gates is called basis gate sets is called universal set gates. What is the universal set gates? Means any unitary operation or gate can be expressed in terms of these basis gate sets. Because user cannot, suppose if I show here, now let me show the generate this one. Before going to the transpilation, let me generate the abstract circuit. Here I'm going to show you two circuits. See here I have created 4-qubit set. After applying the Hadamard gate and X gate, and I have applied this CNOT gates. This is the, and here I'm going to apply the barriers. These one things are called barriers, and between these two barriers there is one thing, IQFT, that is the quantum Fourier transform gate, and this is the abstract circuit. Similarly, I'm going to run another program. On meta actually. This is the abstract circuit. Here, if you see this one, in this circuit, I'm using one Hadamard gate and 4 control NOT gates. And if you see here, these are different gates. This is this gate is called this one. Which one is phase gates? These are all. These are both this one and this one are two abstract circuits. And please note here. Here I'm in this first one, I'm giving the measurement gates, measurement operators, but here I'm not giving the measurement operators. Why? The reason is I will in the third step you will come to know what is the difference, why I am giving this one. This is the abstract circuit. If you see here, these gates and CNOT gate and Hadamard gate is not available. If you see here, these are the basis gates. No? Here, if you see here, only these 7 gates are there, but I am in my circuit, I'm using CNOT gate as well as Hadamard gate. Similarly, in the previous one, these two gates are not available in this Torino quantum hardware. Similarly, what about the Brisbane gate? Similarly, these basis gates are different from the Torino gate. Again, here also, it is not containing, it is not having any CNOT gate or Hadamard gate as well as phase shift gate. So that is the main part. Now, because to convert this abstract circuit incompatible to the target hardware basis gates, we will do the compilation. Apart from this one, there are few more reasons why transpilation is very important. Here, error rates will be, optimization will be done here. And the optimization, and that is again, it's a very big concept. District DAG circuits, layouts will all those come into picture. That is that will consume that. So those details will not going into the details. The transpilation will also reduce the errors. As the number of this multi-qubit gates increases, means errors will be induced into the circuits because of heat generation source. When you process the quantum states or quantum states, heat will be generated enormously. Because of heat generation, the qubit will lose its superposition properties, and because of its fragility. So this transpilation will take care of those activities also. That is the main purpose. Then actually this I have shown you. And these are all the what I have shown. Previously, I am having every open users was given 3 IBM quantum hardware, but they have removed the middle one, IBM Sharebook, they had removed that one. And this is the hardware. Why transpilation? Apart from that, making your abstract circuit incompatible to the quantum hardware. These are all the several hardware constraints, qubit connectivity, noise, and errors. This we will see now itself. These are the hardware component operations. As I told you just now, why every quantum computer generally built on few set of operations. Those combination of set of those operations are called universal gate sets or basis gate sets. Because of universality, we can convert any type of unitary gate in terms of using those gates, universal gates. This is the one, and here this is the code for conversing this one. I will show you the code how to do this one. I will show here. This one we have already executed. Now, if you see here, this backend, this third thing, this line, 9th one. Here it is selecting the least busy. Actually, all open users have been provided with the 2 quantum thing. Within the 2, which one is available for least execution? That thing, that this statement will select that the least available quantum hardware. I'm going to print that quantum hardware which is available. Oh, this I haven't done. Brisbane is available for my execution currently. So here, this is the main thing, which converts your IBM, abstract circuit into the physical circuit. Here you will be having, for that to use this transpilation process, this is the Qiskit.transpiler is the module which gives all the functionalities that are necessary to generate your ISA circuits. For that, there is one class called generate preset manager. Using that class, you will instantiate the preset manager. By running that preset manager and passing your abstract circuit as a parameter, you will get the ISA circuit. This is the one which you have to use. PM is the instance of the pass manager. To that pass manager, I am running the abstract circuit, which it was generated previously. Then after running this one, you will get the ISA circuit. Let me run this one. Now it is being run. If you go here and see in the workload that here, if you see here, this is the job ID that has been created for just now. Okay, now let me see. This is the hardware constraints. After that, this is the qubit connectivity. Because if you see here again in the workload, not workload, compute resource. If you see here, this is the qubit connectivity. If you keenly observe these zeros, nodes are there, no? This is 0, 1, 2, 3. Those are all the qubit numbers. 0th qubit, first qubit, like that, up to 126 or 132 qubits are there. If you keenly observe, every qubit is not associated or not connected with the remaining 131 qubits. So because of that one, qubit constraint will arise, and so that the information processing will not happen as per expected. So in order to do that one, swap gates are included to increase the qubit connectivity. That way, this is what. For IBM superconductor, this is limited to the qubit that has physical connectivity. For multi-qubit, this means we can only run this qubit, insufficient qubit. Using swaps, we can, but there is some drawback of using the swap. Actually, the multi-qubits generally induce more errors. That is the only drawback, and it is expensive also. So to create that, creating the swap gates itself will take is expensive. So we have to, the job of the compiler is to minimize these swap gates. For that purpose, if you see here, one of ECR gate is there. Here it is not there. For IBM Brisbane, it is there. ECR, that will take care of this one. This is the qubit connectivity. And gates. What is meant by noise means unwanted. Anything that is unwanted in that particular field is said to be noise. And here in this case, gate errors, what are the sources of gates? What are the sources of errors or noise means? It is being, one source is from the qubit itself. Qubits are created or manufactured in different, using different technologies, and there may be some lapses because of which qubits may induce some errors. That is one source of error. And the second source of error is multi-qubit gates and single qubit gates. When you compared with multi-qubit with single qubit error with the single qubit error, multi-qubits qubits or gates are more error prone than to the single qubit gates. And what about the readout errors? In the first slide, while showing the architecture, there is an analog circuit which converts your data, binary data, into the quantum phase, quantum states. There, that process is called the encoding phase. During encoding, readout errors will happen. And what are actually for doing encoding, there are three types of encoding. One is called the basis encoding. The second one is the phase encoding, and the third one is the amplitude encoding. And the coherence time, decoherence is also one source of error. Well, there are two types of decoherence. One is called the energy relaxation, and which relates to the energy. For suppose if the qubit is prepared in the excited state, and the qubit will stay there for only for few nanoseconds. Before that excited qubit returns to the ground state, you have to complete your computations. That time is called T1 phase. T1, here I will show you this one. Here if you see here, median T1. This is the relaxation. And the second one is the median T2. Median T2 is the superposition, dephasing a qubit from superposition to the basis state. That is called the median time. These are occur during encoding. These are the errors and sources of errors. So what it will do, the second step of Qiskit pattern, it will convert your abstract circuit and optimize it for better execution into the ISA circuit. ISA circuit is the one that is compatible to your IBM target IBM hardware. This is the one. Here during transpilation, it will take abstract circuit and you will get ISA circuit, instruction set architecture. That is the one. Now let us see about the execution. Now I have executed. Now I'm going to. This is the ISA circuit. Similarly, here also I'm going to execute. This one, what is observable, we will see later. Any doubts, madam?
Participants, do you have any doubts?
This is if you see here, when you compare this one. Yes, sir.
Hello.
Yes, sir.
Sir, can we do this circuits by modeling in a MATLAB?
Sir, I can't get you, sir. Can we do this circuit?
This circuit by modeling in a MATLAB. MATLAB, I'm asking, sir. Can you do this?
MATLAB. One thing, sir. This MATLAB, since we are doing optimized, Dijkstras is one optimization problem that we can do. Yes, we can do it, that one. If you are good in graph theory, you can use. Actually, graph theory is used. See, as soon as 1 minute, sir, 1 minute. As soon as this abstract circuit is fed into the step 2, that means the transpilation, immediately what it will do is it will represent or it will convert this abstract circuit into the DAG circuit, sir. That means directed acyclic group. That will be in the form of just like in the in graphs you will have phases and nodes and edges, no, sir? Like that it will be converted. Yes. It will be converted like that. Manually, you can manipulate, you can add your operations, or if you can delete this one using here in the second step also, sir, in the transpilation. You can do that one, sir. But MATLAB, I'm not sure, sir, whether you can do it or not. But actually, since we can process, we can simulate all our graph models in the MATLAB. We can try, but I'm not sure, sir. But here in visualization, the MATLAB we are using in Qiskit in the last step.
Okay.
But internally what is happening, we don't know. But we can customize our steps. Actually, I have not gone in detail, sir, in the second step, in the transpilation step. Actually, the entire transpilation is divided into 6 steps. One is called the init step. Second one is the layout step. Third one is the routing step. Fourth one is the translation step. And the fifth one is the optimization. Then the sixth one is the scheduling. These things will go, and this is the core. These are the 6 parts. These 6 things are called passes. 6 passes we'll call it. These are the main thing. You can manually manipulate it if you're good at strong in mathematics, especially in graph theory. You can do it, sir.
Okay, sir. Okay. Sir, can also I have one more doubt. Sir, can we
Yes,
also the same thing can code like we can model develop mathematical model. You can code in either MATLAB or in Python direct. Suppose I do not want to show these circuits. I do not want to simulate this circuit. Can you do by coding this modeling and coding this one?
Sir, can you please repeat it, sir?
Yes, sir. Yes, sir. Suppose I'm taking one examples like XGate circuit. Suppose I want to develop a mathematical model for this one, and I want to code the same in either MATLAB or in Python. So can we do that by coding also, or we have to use this way? What we are saying like that only?
Yes, sir. One thing, sir. Here there is one more quantum at the starting. Why you are using why Qiskit is the front runner in the Qiskit pattern means here you will be having one quantum Qiskit dot quantum underscore info package is there, sir. A module is there. There you can extract all your information, whatever you want. Whether if you want to extract if you want to see the state in generally the state will be in the column vector, but you can convert that one into the density matrix also. And yes, sir, you can do it. Whatever you want, you can do it mathematically. All those mathematical functions, methods are available in the Qiskit dot quantum underscore info package. Suppose, sir, while executing, so see 1 minute, sir. Suppose after executing the first 3 gates in this quantum circuit, if you want to learn, if you want to know what is the quantum state of this one, either in the density matrix, or you can extract that information by using that methods available in the Qiskit dot quantum underscore info package module. You can extract the information along with the classical feed forward instructions.
Thank you.
Is that clear, sir?
Yes, sir. Definitely, yes, sir. Actually, I was just starting that part only. That's why I'm asking, sir, because I'm doing modeling.
Yes, sir. Yes, you can extract it. You can extract the quantum information. Generally, here what we are saying, suppose input state we are giving some 001, and the extra after performing the output we are extracting. In between the input and output, we can extract, and based on this information, you can change the qubits also. That is called dynamic circuits, sir.
Yes, sir.
That is called dynamic circuit. While executing, you will monitor the values. Based on the values, you can change it. A dynamic circuit, we will call it. These are all called the static circuits.
Okay, thank you, sir. Thank you.
Okay, welcome, sir. Madam, any other doubts, sir?
No, sir, I'll ask once I'll get then again ask. Just proceed, sir.
Okay. Okay. Up to here. Okay. I'm proceeding forward, sir. Now, once your ISA circuit is ready, then it will be, we are going to enter into the third step of that is called the Qiskit circuit execution. Actually, sir, here the quantum circuits generally will give two types of outputs. One is the probable distribution for a chosen set of qubits, and the second one is the expectation value. Okay, for both, I will show by executing the two circuits. And now I told you, there will be the primitives in the first, second, third, fourth step in the features of Qiskit. There I have given that circuit execution pattern has been clubbed into the primitives. That means sampler and estimator pattern. Here it will come into the picture. Actually, here in Qiskit, we are having two types of primitives. These primitives are called, the number one is called the sampler primitive, and the second one is the estimator primitive. The estimator primitive will give you the output in the expected values. Expected values, if you want the result in the form of expected values, then you have to use this estimator primitive for your execution. And if you want a probability distribution over a set of qubits, selected qubits, then you have to use the sampler. And apart from choosing those primitives, again you need to choose in which mode you want to execute your program. That here we are having three types of modes. One is called the job mode, batch mode, and the third one is the session mode. In the job mode, user can submit only one job at a time for execution. But in session and batch mode, user can submit more than one job at a time. But what is the difference between the job mode and the session mode? That is the one thing. In the job mode, suppose if I send my batch mode, batch execution, similarly, at the same time, concurrently, other people or other users can submit their jobs either in the batch mode or job mode or session mode. That means the quantum resources are being distributed or can be used by all users at a time. But in the session mode, once if I submit the session mode, my jobs in the session mode, then third user cannot, that all the resources will be freezed to that particular user. That means the other users has to wait for till my jobs session mode is completed. That is the only thing. And the jobs which are being submitted in these modes are called workloads. Any doubts, sir, up to primitives and job modes? Now we'll see
No, sir.
Okay, okay. Now in this step, we are going to take here in the third step, we are going to take the ISA circuit that was generated in the step 2 of the Qiskit pattern, and we will execute here based on the output output that we are waiting for. Here, if you see here, this one. Here, this is the estimator. In the estimator, 1 meter. sampler will let me convert. Let me do it. This one I already done. Now this is the pub. Here, if you see here, pub. What is the pub means? Pub is nothing but what it will take your, suppose if pub is a collection of some tuples. Within tuple, there will be you will put your ISS circuit, and if at all, if it is, that means if you are submitting your variational hybrid circuit, those parameters you can submit. Since my circuit is not a variational hybrid circuit, I am giving the none, and this is the number of shots I want to execute. This entire thing will form the pub. Suppose if I want to run more than one circuit, means you just create a tuple consisting of that circuit along with the parameters and the shots, and you just create a list and assign that one. This part is called pub. Pub is nothing but primitive unified block. Be sent for running here. Here I want to, here what I am doing, using this runtime, I am importing this sampler v2 class, and I am creating the instance of that sampler, and by sending the backend, which is there, IBM Brisbane, I think that is the least available. And in this sampler, I am using the run method. I submitted this pub, and it will be run. If I run this one, pub is not run. Okay, let me run. Now, if you see here, see, status is pending. Still it is in queue. Status is pending. If you see here, the program which I am submitted, it is a sampler. How many pubs is there? How many primitive unified blocks is there? I have submitted only one pub. So it will be showing only one pub. And if you see here, how long, when it was created that time at this one, and still it is pending. Like that. So let me suppose, let me execute this one also, so that here, let me execute this estimator also. See, as soon as I submitted this job now, job ID is created. And if you see here in the workload, you will see all your, still both are in pending. And both are being submitted in the, for execution on the IBM Brisbane. And if you want to details, only these things, remaining details you can share, you can write scripts. Once that is executed, we can see the details of our execution. Sir, any doubts? We have to wait for execution to complete. Meanwhile, you can ask any doubts. Not only this one, actually, Yesterday, Karthik Ganeshan has told that the importance of mathematics. Here, I will share one document to Prabhadevi Madam so that she can circulate to you, which is very, very important. That is the C0 gate. How can, if you are good at mathematics, means you can convert this entire phase circuit using C0 gates only, not any other things. So please ask me any doubts, sir. It is.
Participants, if you have any doubts, please.
Yes, ma'am. Sir, actually, suppose we are doing suppose any modeling. So how
Yes.
beginning in that, suppose we have any value like suppose 1 to 10 we have a value 1 to 3 or 1.1 like that. Some 10 value we have. So suppose I want to apply this input in a C0 gate. So how we can use here? That is my
Yes.
basic.
Yes, sir. Having before that one here, no, 1 minute, sir. I will show you. In the first, I think in the slide, that is the place where here that 1 to 10 values will be converted into the first here it will be converted into the binary data, sir. From here, yes, sir. Here, before going that binary data into this chamber for processing, here there will be analog circuit converters is there, sir. There it will be using these binary digits will be converted into the quantum state, sir. That is called the encoding part. Encoding. Actually, here we are having 3 types of encoding. I have repeated. I am going to repeat this. One is the basis encoding. The second one is the phase encoding, and the third one is the amplitude encoding. After that only it will be the phases will be sent into the chamber for execution. And once the execution is completed, the output will be sent back to the same thing where it will be converted back into the binary data.
Sir, how are you deciding the phase? Like suppose we have a data set, X and Y data set here. So how we can decide
Yes, sir.
the phase?
Yes, sir. That is very good question. If you know about that, again we have to go into the complex numbers, sir.
Oh, yes, sir.
Complex numbers. There
complex.
in that one, cubic root of unity is there, one small concept.
Yes, sir, I know
From
that
there,
one.
from there, yes, sir. From there, sir.
Yes, sir. We have 3 roots like 1 omega square that way, or 1 alpha
Yes,
alpha
sir.
square.
Yes, sir. From there, since this complex in the complex numbers, we are using only sines and cosines.
Yes, sir. Yes, sir.
Because and these are all out of phase. Sines and cosines are out of phase.
Euler's formula also, sir. Euler's formula can you apply here?
Sir?
Euler's formula, E power I theta.
Yes, sir. Yes, sir. Instead of using cos theta plus I sin theta, you can use e to the power of I theta. Actually, the Euler's formula is you have to express in the form of polar coordinate. That is polar coordinates. E to the suppose if since we are dealing with the unitary circuits, we are going to remove that r theta. Actually, the polar form is r into e to the power of I theta. Right?
Yes, sir.
Since here we are dealing with the Bloch sphere, which is having the unit radius, we are removing that r and we are with e to the power of I theta. And that one, yes, sir. And e to the power of I theta, if you want to convert into the matrices form, then you have to use the Taylor's series.
Yeah, Taylor says that we have
Yes, sir.
univariable Taylor says
Yes, sir.
or
If you yes, sir. If you keenly observe that e to r e to the power of I theta, theta is the phase
yes sir, yes sir.
that will be converted into the matrices.
Yes sir, that we have our matrices that whatever we have
Yes, sir.
get that we
Using
can write.
Taylor's theorem, you can do that one. Again, using Taylor's theorem, suppose if there is only one gate, I think yesterday or the day before, yesterday Karthik sir has touched this one, right? Any gate can be expressed as a product of 3 gates.
Yes, sir.
That is called decomposition. Again, when decomposition, you have to go into the linear algebra. That means
Yeah,
by
yes,
force of,
yes,
yes, sir.
right.
Everything is interlinked, sir.
Yes sir.
Is that clear,
Sir,
sir?
one more. Yes,
Yes,
now
sir.
it's
Yes,
clear.
sir.
Again, I have basic this confusion again. So it's a different one. Suppose we are assuming that properties of that quantum properties that suppose sinusoidal function we are using that e power j omega j bracket omega t plus k into z or k into x and k into y, whatever the way propagating that particular directions x y z. So in our quantum,
Sir, please repeat it, sir. I'm not.
okay, so okay, sir, I'm repeating, sir. Suppose, sir, we have a sinusoidal wave like e power j in bracket and then omega t plus or minus kz. Z is the direction of wave propagating, sir. So in that case, sir, here we know that omega is a function of time and as well as frequency both. Omega is a shear frequency. 2 pi f or you can add 2 pi by t. And
Then you,
k we can write 2
yes,
pi
sir.
by lambda. 2 pi by lambda
Then,
that we can write. So yes, sir. So if our quantum particles depends on the time or displacement, how we can correlate here, sir, that in circuit? Because anywhere we are using the that
yes, sir.
property.
Yes, sir. I got it. Using quantum Fourier, you can easily do that. For quantum Fourier transform, you can easily convert it. That means here you will be having time space domain that you are converting into the frequency domain. Using Fourier transform, you can do it, sir.
Yes, sir. Okay, okay, sir.
Even the Hadamard gets so simple, sir. I shown here in this circuit. Why are I using this? 1 minute, sir. I will show you one more thing. I don't know. Actually, they have changed this. It is not running, sir.
Okay,
Let me check.
sir.
Because
Actually, sir, are not available easily, sir. So we are doing modeling and only coding like that.
One thing, sir. One thing. The Hadamard gate, you know the purpose of Hadamard gate.
Yes.
Hadamard gate, sir.
Yes, sir. Yes, sir.
That means in the computational basis, ket 0 and ket
For
1.
for complex property, generally we are using that.
No, Hadamard gate is used to induce the superposition, sir.
Yeah, super 2 where we are going
Suppose
to impose
if my quantum state is in ket 0, if I apply the Hadamard gate, then I am, if you think that one, my ket 0 means it is in the computational basis. Computational basis is one space, say. Within the space, by applying the quantum Hadamard gate, I am converting this computational basis to another space called the superposition space. This Hadamard gate itself is one example for quantum Fourier transform. If you think, of course, if superposition we will designate as ket 0 plus ket 1 by root 2, right?
Yes.
Which is equal to plus state, which is equal to plus state. If you convert, if you show instead of ket 0 and ket 1, if you use ket plus, then we can visualize it as it is in another space. That is where some principle is there. You cannot extract two properties at the same time. That means you cannot extract the speed and space and angular momentum at the same time.
At the same time, that where positions
Yes.
of the particle and that
Yes.
moment of particle you can't predict at the same time. That's why we're
Same
using the
time.
high.
In other words, in another word, you can create like this. You cannot extract or you cannot measure both superposition and you cannot measure the state of a quantum system in two spaces at the same time. That means in the ket state you cannot measure, and you cannot measure the state in computational basis space at the same time. Either you have to choose either computational basis ket0 or ket1 space, or ket plus or ket minus space. You know how to do what is meant by Fourier transforms.
Yes, sir. Fourier transform, just basic formula that we are going to convert any single time domain to frequency domain, but condition that that you have very select condition that should be satisfied, then we are going to use the Fourier. Otherwise, we can't use Fourier transform.
Yes.
There is some limitations in that Fourier.
Yes.
And the problem is that by using, sir, once we are going for the localization of your whatever signals. So once we can localize either in time or as a frequency. So this is also drawback of the Fourier. So in that case, we are using the wavelet transform that we can localize all those both signal time domain as well as frequency at a time. So that also I mean doing some work on that basis. This Fourier and wavelet also I'm using the quantum. That is I'm doing currently. So
okay, sir. Now both jobs are completed. Let me show you the results, sir.
Okay.
Right. Here, if I run here, now I'm going to retrieve the job ID for this one. Here, this is the job ID. If you see here, this is the one. 607. These two are the job of 6G. The 6G. And this is the another job for another program. This is the 60. If you see here, after the job ID, you will be having which program, type of program, whether it is a estimator or sampler. Then I'm going to retrieve the job details. How can we using this statement? We are going to retrieve the details. Here I will explain you this one, what this means. Similarly, here also you will retrieve the same thing. All the job properties are there, will be here, but I want only the here for estimator, for sampler I want the distribution, probability distributions over a set of qubits. Here I'm going to retrieve. Here if you see here, C is there. No, actually the data after executing, the result will be stored in the form of data bin container. Here if you see here, data bin. Similarly here also if you see here, where it is, pub result. Here it is, data bin. But the internal structure, there may be slightly different. Here if you see inside the database, EVS is there. For estimator, it is estimator values sampler. That is the full form. Here you will get the details in the form of estimation, in the form of values. But sampler you need to get in the form of probability distribution set. 1 minute. result data is not job result. Sorry. One minute, I will show you something. Using this C value, you can get all those probability distribution. Somehow it was missed. I'm not able to show. Here, then plotting this results in the for visualization, you can plot this one using this visualization. This visualization, you can plot your details. Something is missing. Like that, sir, we can do it. Actually, that code is missing. And what are the various types of visualization means you can see not only your abstract circuit, you can see your layout, you can see the DAG circuit, and you can convert your circuit from one using the circuit converters. You can convert your circuit from ISA circuit to the DAG circuit and DAG to the abstract circuit. Everything you can do that one. These are the things we can do. Even this hardware coupling, actually this coupling here I have shown you this in the back end. These things is called coupling map you can generate from this one. But here this coupling is being shown in the form of lists of lists. These things. Where it is. Compute resources. We type here. This is. And if you hover the mouse over this one, you will see for every qubit properties also you can see this one. I will show, I cannot show this one, 1 meter. I will show the backend properties. Target is there. Yeah. I cannot run this one, but if you see here, see number of qubits. What is the duration for this qubit, 0th qubit? What is the duration? It will be in excited state, and what error rate, or how much error that particular qubit will consist of. Similarly for qubit 1, like that. And gate wise, suppose for this gate, you get, if it is applied in qubit 0, this is the error rate that will be induced by gate U into the qubit 0. And because of this one, the qubit can stay in the exciting state for this one, for this nanoseconds. Similarly for CX gate. CX gate, when applied, since CS gate is a 2 qubit gate, when it is applied with G in 0th and first qubit, these are the properties. Like that we can get in it. These are the durations. See here again. Like that, sir, it is a vast subject. In one day or even in it will take to get at least it will take around 6 months to get habituated to this Qiskit programming like this. Sir, any doubts, sir? Actually, I will send this Jupyter notebook as well as this PPT along with these two codes. By adding this, I will modify this one, and with the results I will send to the Prabha Devi madam. She will circulate to all of you. And not only the circuit visualization, you can do it as a result visualization also. Actually, here in result visualization, actually so far what we have done after running, we will formalize the states, quantum states in the form of column vectors. That we will call state vectors. That is not the only way to formalize your states. You can use a density state also as well as stabilizer states. This stabilizer states will be generated using ECR gate. ECR gate I will show you here. Here, if you see here, for this Brisbane, you will be having ECR gate. Madam. Hello. Tell me, madam.
Sir, unmute yourself, sir. Jaikumar, sir.
Hello.
Answer. Yeah, sir.
Yes, madam. With this, I will complete, madam. I will send all the material to you so that you can circulate, you can distribute to the attendees, madam.
Yes, sir. Sure, sir.
Okay, madam.
Thank you so much for this more engaging session, sir.
Okay.
Yeah.
Okay, madam.
Thank you.
Okay, sir.
Yes. Shadab, sir, can you hear me? Shadab, sir.
Yes, ma'am, I can hear you.
Yeah.
My voice is clear to you or not?
Yes, sir, it's clear.
Okay.
Please share your screen, sir. I made you as a presenter. I hope you can share the screen.
Okay, ma'am, let me check. Just one sec, ma'am, sharing.
Can you able to share, sir?
Yes, ma'am, just 1 second.
Yeah.
I hope my screen is visible now.
Yes, sir.
Okay, perfect. Let me start.
Yes, sir. Sir, welcome you, sir. Dear participants, this is our next session. This is the last session for the day. And I welcome Shadab Hussain, sir. He's from Illinois. And He has been expertise in the Gen AI as well as with the quantum computing, and currently he's working at Mathco at US. Is working there, and he has around. He was a recognized Google developer, and he's around more than 9 years of experience. And his expertise is one of the TEDx speaker as well. In different types of different activities pertaining to this AI as well as this quantum, this one. And over to you, sir.
Thank you, Pratibha ma'am, for the invite. I hope my screen is visible, right?
Yes, sir.
Okay, and my voice is still clear, right? Any challenges in hearing?
No, voice is clear, but screen is it's empty screen.
Empty screen.
Anita ma'am, can you able to see screen?
Yeah, yes, ma'am, it's visible.
Yes, sir. Please
Okay.
proceed, sir. I have some issues with
Okay.
internet. Now it is visible, sir, for me as well.
Okay, perfect, cool. So, good evening, everyone. Let me start. And I will be shifting between the slides, like I was not able to compile the slide content in one slide. So let me make it in the presentation mode first here. Okay, so good evening, everyone, and thanks, Pabha ma'am, and for the invite. Today, we are going to delve into a topic which is rapidly reshaping our technological landscape, that is the convergence of quantum computing and generative AI. And we are sort of like standing at a pivotal moment, and 2025 has been declared by United Nations also as the International Year of Quantum Science and Technology. So we have seen incredible achievements like from Google's Willow chip demonstrating unprecedented error correction capabilities to Microsoft's groundbreaking work with topological qubits as well. And simultaneously in the field of generative AI also it has also moved beyond early adoption, and we are seeing a significant majority of enterprises they have started adapting it, and they are like seeing the tangible returns on their investments. Right. So the whole purpose of picking this topic was so that we can talk a bit about like quantum generative AI. Like we can't leave the generative AI and both of the like what is the convergence point for these technologies are. And so that will the core thesis today. And like we are and we are moving beyond single domain applications now. And true exponential capabilities will be lying in the multidisciplinary convergence of quantum and AI, right? So this synergy will hold the key to solve some of humanity's most complex challenges, transitioning from mere experimentation to real world impact across different industries. So before I move ahead, like a bit about me, like Prabha has already given the introduction. So I work as a lead engineer at Mapco for Data and Gen AI. I co-founded Quantum Computing India community back in 2019. And uh, like whatever work I do full time, like apart from that, I'm pursuing research also in the quantum field, specifically focused on quantum machine learning side. And I collaborate with the people and try to share the knowledge wherever I can with the people. So let me switch this a bit. Yep. Okay, so that's a bit about me. Starting with first we'll try to understand what existing quantum landscape we have in 2025. So this year has been marked by several significant breakthroughs. Google's Willows chip, for instance, I mean, they represented a monumental leap in quantum error correction. And this technology is crucial because it addresses the inherent fragility of the qubits, allowing for more stable and scalable quantum computations. So far we have seen that quantum computer people have been working and developing and trying to improvise the hardware from that work is going on from years. But we are seeing accelerated development in that domain as well. And while we are scaling the same way, the error margin is also getting increased, where the Velo chip was able to demonstrate the capability to reduce the errors exponentially as we are scaling the quantum systems. So this was one of the major breakthrough, like you can say, towards the fault tolerant quantum computers. After that, like we heard about Microsoft's Majorana chip. That was also, I mean, that also made a remarkable strides with this chip, and this was the world's first quantum processor, which was powered by topological qubits. So this approach basically promises enhanced stability and error resistance, and Microsoft has successfully created and entangled 24 logical qubits with atom computing. So this was the robust one of the like quantum systems which is a bit robust, and that was also very major breakthrough in the industry. Beyond individual chip advancements, also if we talk about it, we are seeing the rise of sophisticated hybrid systems. So companies like Quantum Machines, Nvidia, they are collaborating on platforms like DGX Quantum, which achieves like microsecond latency between quantum and classical processing. And these kind of like seamless integrations are very vital for practical applications, which allows classical computers to manage and optimize quantum operations efficiently. And we have seen a lot of government investments as well, like be it US, Australia, or any other country. So Australian government, I think they invested around 620 million investment in PsiQuantum. Uh, Illinois, like it's a state in United States, they committed like around $500 million for their quantum park. Similarly, Japan also announced like around 7.4 billion commitment for accelerating quantum research and development, and they have been focused on like the tech advancements along with the sustainable practices. And these investments are not just about funding labs, right? They're about building infra talent to bring to the quantum world. And this is also more of like we are moving from theoretical realm of quantum into practical and real world applications. So some of the like progress, if we look at like, I mean, these progress are not just about chips. It's also about like scaling up. So in 2025, we have seen like impressive advancements in qubit counts and system capabilities. Atom computing, for example, has pushed the boundaries with 1,180 qubits around neutral atom system, and they demonstrated a significant leap in the number of stable qubits which were available for computation. Similarly, D-Wave, they also, with their Advantage 2 system, they have been boasting with 4,400 qubits. And D-Wave, if someone doesn't know, like they are quantum annealing based, they have annealing based quantum computer. So that's why like they have higher number of bits when it comes to logical or qubits or superconducting quantum bits. In that case, we have still limitations, and companies like IBM, if we talk about, they have been able to achieve like around the system with around 1,121 or 1,021 qubits. So these are the advancements, right, which are driving a rapid increase in industry investment, and quantum computing companies have already started generating the revenue between 650 to 750 million dollars in last year, which is expected to surpass like $1 billion in 2025. And this surge in investment reflects growing confidence in the like commercial use cases of quantum technologies. But still, like whatever the rapid growth is happening, with the growth we have its own challenges as well, and we have a significant concern about the quantum skills crisis. A lot of companies have been doing the research, analyzing the data and all, and which indicates that 76% of leaders believe that there is a shortage of skilled professionals, like which we are going to see like in this field. So there is a critical need for talent development and educational initiatives to bridge the gap between the technological progress and human expertise. As quantum systems will becoming more powerful. We need more individuals who can design, operate, and apply these systems. With more like expertise. So that was a bit about quantum. Let's talk a bit about generative AI now. So in 2025, we are moving beyond the conversational capabilities of early models like ChatGPT era or whatever we had, right? And from that era, we are sort of moving towards the autonomous agents. And these new generations of AI is not just responding to prompts; they are handling complex tasks also independently, making decisions and even learning from yeah, even learning from their interactions. It has improved a lot. Like if you remember when the first time the ChatGPT was announced, the responses, the capabilities, and nowadays if you have started using agentic workflows, using the tools like Cloud or Vibe coding, if you have been like, if anyone is actively into coding and also if you have used Copilot and all, you'll be knowing that, right? So Deloitte also predicted that in 2025, a quarter of companies already using generative AI will launch agentic AI pilots or proof of concepts at least, which will be signaling a significant shift towards more sufficient AI, more self-sufficient AI systems. Okay, and accompanying these rise of autonomous agents are significant advances in AI reasoning capabilities. So models which are now demonstrating the ability to break down complex problems into logical steps, they will be showing their work and providing more transparent and verifiable solutions. So still like whatever system, whenever we run, earlier if you remember, we were not getting the sources cited on the results, whatever we're getting from the these kind of tools like ChatGPT or Gemini or Cloud. But they have been improvising on the systems, and whatever piece of information gets displayed to us, uh, if we ask or sometimes by themselves also, the response includes sources also as a link embedded to the response, whatever we get from there, which is sort of like building the trust, what source we are exactly bringing in to fetch the information for the prompt we are passing to the model. Also, enterprise integration of GenAI is like accelerating with a very fast pace, and we have been seeing that 70% of Fortune 500 companies have started using Microsoft 365 Copilot for different tasks, like if any workflows we have to automate for like content creation, we can use that. And also there is a 71% of organizations are regularly using GenAI in at least one of the business functions. So all these numbers, percentages, right, they're indicating widespread adoption and a clear recognition of its value in enhancing productivity and efficiency across the board. So now like GenAI or agentic AI systems are not just limited to a single department or single within a single department of an organization, but at, like approximately each department in an organization have already started using GenAI or AI tools in some or the other forms. So be it the marketing team, sales team, finance team, developers, it has it's already going to the next level. So the question is like the people who can understand like how to use AI efficiently and better to make themselves productive and stay ahead in the curve, they will be like the experts. You don't have to know how the AI is getting created, but we need to know like how to use it efficiently and in a better way. So that's where the Gen AI is heading. Like we are already seeing the companies moving towards the autonomous agentic AI workflow systems to handle the tasks end to end. Next is let's talk a bit about uh, technical leaps and market transformation. So advancements in Gen AI have not just, it's not just about new applications. They are rooted in profound technical leaps, and they are driving significant market transformation. So one of the most impactful development which we have seen is like increasing the sophistication of multimodal capabilities. Every now and then we keep hearing about a new version of the model announced by some company, right? Sometimes like you will see OpenAI launched this version of the model, like recently they launched GPT-5, I think, right? After that, like Gemini launched Gemini 2 point some Pro, like that. Then Cloud will launch some other model. So we are seeing very fast updates in this industry where companies are building the model, sophisticated multimodal capabilities, and they're launching in the market. And multimodal are like, if you don't know, I mean, they have the capability to process and generate information across various formats like text, images, audio, and video. And it is becoming integral to like every application across industries. So this allows for richer, more nuanced interactions and more comprehensive AI solutions as well. And these kind of improvements are responsible for directly translating into efficiency gains and substantial returns on investment. At the end, like whatever company is going to invest in this technology, they look for like what value they are going to get in return from this investment, right? So companies are already seeing like those efficient gains and substantial returns on the investment. So like still some of the pilot programs like in the industry, they are facing the challenges. The overall picture is like clear. Gen AI adopters are seeing significant returns, and based on the data, the average ROI is close to like 4 times the investment what they are making, like with financial services leading the way at like around more than 4 times, like that is close to I think 4.2 times, like if you look at this graph here. Okay, and this demonstrates that when implemented strategically, GenAI is powerful engine for productivity and profitability both. And if you look ahead, the economic impact is projected to be immense, and by 2030, AI adoption is expected to drive a staggering $19.9 trillion economic impact globally. That is like $20 trillion global economic impact we'll be seeing by 2030, which is going to contribute to 3.5% of the global GDP. Okay, and this is not just about like automating tasks like what at times it will build the perception. It's also about like how fundamentally the industries are getting reshaped and recreate and are creating new avenues for growth and innovation. Right, a lot of like old process, old way of working are getting discarded, and companies are coming up with new ways of like be at the workforce, be it for like driving the business and all. So most of the organizations, like around 71%, they've already started integrating Gen AI into their business functions, understanding the like urgency and importance of it. And they're leveraging multiple tools, or they're building in-house tools based on like whatever their requirement or use cases are. Next, let's talk about like we have talked individually about quantum and AI. So this brings us to the core of our discussion today, the powerful convergence of quantum computing and artificial intelligence both. And this is not just about two advanced technologies existing side by side. Okay, it's like about their synergistic interaction, which is going to create the capabilities far beyond what either could achieve alone. Okay, so technically, we are sort of like seeing the fascinating developments in both the worlds. We have seen like classical neural networks are now being used to like approximate quantum states, effectively serving as like intermediary computational layers that bridge the gap between classical and quantum domains. These kind of advancements or usage or applications also like allows for more efficient interaction and control of the quantum systems. Conversely, like AI is becoming central to quantum research itself, and particularly for the error correction algorithms. So I don't know like what level of hands-on or quantum programs you have gone through, but there are two sides of like AI and quantum. Like AI is getting used for quantum as well, and quantum is also getting used for the AI. Okay, so when we talk about like how AI is getting used for the quantum, that is like quantum error correction algorithms, we are sort of like using AI-driven algorithms, which are crucial for identifying and mitigating those like small errors which we inherit in the quantum operations, which in result are making the quantum systems more robust and reliable. Furthermore, if we talk about like for progress on the quantum side, then quantum machine learning, they have been uh, promising towards like exponential speed up for certain type of AI problems by leveraging the unique quantum mechanics of properties like superposition, entanglement, and interference. And this is expected that it's going to revolutionize the fields like drug discovery, material science, and complex optimization. Okay. In terms of like if we talk about real world integration, we have been witnessing the significant progress, and real time quantum error correction and AI assisted calibration are achieving like sub 4 microsecond round trip speeds. Okay. And which is enabling sort of like more stable and coherent quantum computations. Hybrid models are also emerging that leverage quantum computing for complex optimization tasks like GenAI assist in problem formulation and solution exploration. And these collaborative landscape is fostering exploratory partnerships between major AI players like OpenAI, Google AI, and leading quantum startups. And all are working towards unlocking the full potential of this convergence. So let's talk a bit about like in the healthcare, what are the use cases and what multidisciplinary applications we have been talking about. So if we look for the multidisciplinary applications of quantum and Gen AI, right, they are poised to revolutionize various sectors, with healthcare leading the charge. And in drug discovery, quantum computers are uniquely suited for molecular simulation. They can naturally simulate quantum mechanical systems that encode binding interactions, offering unprecedented accuracy in predicting how molecules will behave. This is also sort of like a game changer for identifying new drug candidates and optimizing the existing ones. If you remember, like earlier, I mean, it's still it like the companies who are using like classical computation or supercomputer side, it takes months of time to simulate one molecule or to find one molecule of for a particular drug as a cure of a disease, test it out, and then sort of like we finalize whether that drug is suitable for that thing or not, which is getting speed up with the help of the quantum computer. And one of the clinics like Cleveland Clinic in US, they have 52 research products which is using quantum. And with their first study, they started with the protein structure prediction, which is already published. Like if you'll go and search like Cleveland Clinic protein structure prediction paper, you will find it. And they have demonstrated the tangible progress in that area with that first research. They have like other like total in total they have 52 research projects going on. If we talk about the diagnostic excellence, right? So that is another area where this convergence is like showing the advantage. So quantum computing, in which I mean, quantum computing can be used to improve the medical imaging through advanced sort of like capture finer advanced techniques that can capture the finer details in comparison to like whatever existing machines we have, right? So if we have the much finer images of like the scan or like CT scan, whatever we are going to perform, obviously that will helps us in more precise diagnosis, right? And we can sort of like use quantum artificial intelligence for pattern recognition and allowing for the like processing of vast data set from the medical records and imaging, so that the diagnosis and treatment planning can be assisted and complemented with better speeds and computation. So we have already started seeing like a lot of research papers making use of quantum machine learning algorithms or quantum neural networks across different healthcare problems like breast cancer, brain tumor, lung cancer, heart disease prediction. People are like researchers from the academia or from different labs. They have been trying to sort of like pick some data set and design quantum algorithms or make use of the quantum machine learning algorithms, run those on the actual quantum computer, see the results, and on some of the use cases we have seen that like quantum machine learning algorithms have also been able to achieve decent accuracy for some of the use cases. They are not like fully there where we can completely trust them. Like they can't be just deployed because medical or healthcare is a very sensitive domain, and we can't take the chance of like error over there. But this research papers or whatever the work is getting done by the researchers is the groundwork for the future work or future advancement, so that when we have more better scalable robust quantum systems, these algorithms can be scaled with much higher precision to get better accuracy and all, right? So this is a laying foundation. We are laying down the foundation for the future work. The third domain where in the healthcare we are seeing the use of quantum is like the personalized medicine. Quantum computing can optimize that personalized treatment plans by analyzing different factors simultaneously, including sort of like patient's genetic data, lifestyle, response to various therapies. This will be sort of like enabling more tailored and effective interventions, which will move us closer to a future where healthcare is truly individualized. It's still like such kind of like personalized medicine or treatment plans are not available. We have the doctors who understand and do the like diagnosis. They will be knowing our past medical history. Based on that, they come up with a treatment plan. But the personalized medicine is a very big field where we can have truly individualized healthcare systems to take care of like us. Next field, we are going to talk about the financial services. So before that, like if you have any questions at like any point, feel free to like post that in the chat. Maybe like once I'm done with the slides, I will take up those questions. Next, let's talk about the financial roadmap. So beyond healthcare, we have been seeing a huge adoption in the finance industry as well. And they have been also one of the like earliest adopters of quantum technologies. And quantum finance, if we talk about, right, it's not, that is not just a theoretical concept. If someone would have seen like if someone would have been saying this like quantum finance is still a theoretical concept 3 years, 4 years back, then that would have been the different scenario. But with the current advancements and adoption, whatever is happening, we are seeing the like whatever work people were doing to publish the papers in collaboration with labs and the companies, we are seeing rapid movement into the practical applications now. For example, I will take the example of the quantum support vector machine algorithm itself. They have been showing promising results for some of the complex risk modeling, which allows financial institutions to better access and manage market volatility and credit risk. So IBM has been like IBM is one of the leading company in the quantum domain, and they predicted that quantum computing will have a significant impact on pricing models and business optimization before this decade. And that means before 2030 ends, we will see some of the like significant impact in this industry. And the impact will like where all we can see is like more accurate asset pricing, improved fraud detection, enhanced portfolio optimization, right? So these use cases we will see emerging more into the production. But at the same time, the impact sort of like extends like far beyond finance, and we'll be seeing its use cases in material science. Quantum applications are sort of like accelerating research in areas like carbon sequestration and the discovery of like novel materials with unprecedented properties. Also, like this has profound implications for sustainable and industrial innovation as well. Like, and if you talk about like quantum computing, like they have been like people are working towards like how we can accelerate energy optimization use cases so that we can design more efficient energy grids and renewable energy systems, right? So some of the use cases like a windmill optimization problem is like one of the examples of like how we can harness the energy properly. in the field of like mining or those kind of use cases, how the pipeline connectivity can be like done from point A to B and so on, like how we can optimize that network of flowing the fuel, be it the petrol, diesel, oil, gas, whatever it is, right? So those kind of optimization also can be done easily with the help of quantum computers. So furthermore, like if you talk about the quantum machine learning, it is also set to revolutionize logistic industry as well through advanced optimization algorithms. There's a in supply chain industry also we have like optimization problem, the like optimization of the shipment vehicles, right? That is one problem which can be tackled easily using the quantum computers. Then if you know the like big warehouses like the one by Amazon or Walmart or such big companies, right? They have autonomous vehicles, right, which helps us in moving the packages from one place to another, or like just like whatever instructions have been given to them. And often, like the number of those autonomous robots, whatever we see in these kind of big warehouses, is very huge. So often they have to wait for the other autonomous vehicles to pass by, which waste their time, right? So how we can like optimize their sort of like route so that they don't have to wait. And this is actually real cases today. I remember one of the companies partnered with some e-commerce company and they worked on that use case and they were able to save the average waiting time of these autonomous vehicle by 15%. So such kind of like implementations we are seeing like in the industry. Okay, like sorry, yeah, I was here. Yeah. So such kind of like implications we are seeing in the industry, and further we have the implementation roadmap as well. So how the organizations can prepare for this quantum AI feature, right? So we have to begin with a clear implementation roadmap, and that responsibility is not just limited to the organization, even like with the research institutes or academia also. Thinking of like what problem, I mean, the different levels of like how we can, the different problems, right? And there'll be different priorities for different problems. So we need to think of like what can be like prioritized, what can be achieved in near term, what we have to wait for in future, but we can lay down the foundation for such problems. So it starts with like the clear implementation roadmap, and Microsoft, for example, they have prepared a quantum ready program which is designed to equip business leaders with the tools and insights which they need to access quantum opportunities within their organizations. So this involves understanding the potential impact, identifying relevant use cases, and developing a strategic approach for the adoption. Talent adoption, if we talk about, it is another critical component, and the demand for quantum scientists, I mean, with not only technical expertise, but also having some business acumen and strong communication skills is rapidly increasing. And that's why the organization needs to invest in training and education programs to cultivate this interdisciplinary talent pool. And this also means that fostering collaboration between quantum physicists, computer scientists, and domain experts to ensure that like the technology is applied effectively to the real world problems. The same gets applied again, like I will like try to give the example of academia as well. So if like in academia, if like professors or PhD students or postdocs or scientists or researchers, they are pursuing research, right? They should not limit their research just under their work. Look for like how you can do the collaboration with other department who is bringing some other expertise, some other domain of business also, like finance, healthcare, security, whatever you can think of, right? Try to sort of like form a group of like inter people from different skills for a project, bring those expertise on the table, and then try to formulate like whatever problem you're trying to solve. Utilize those skills and work for solving those problems in a better way. Because oftentimes I've seen, like especially with the researchers, that the collaboration with the actual like a person who is going to use the technology, whatever they have been working on, it sometimes it gets neglected, or sometimes when people communicate also try to start that channel, it's at the very later stage of their research, which like already you have done 60-70% of the work, and if they will give the some input which can contradict the work whatever has been done so far, then most of the time you'll see that researchers will not be willing to go back and then do the work again and like achieve the right results, right? So instead of like focusing on like numbers and like, I mean, efficiency and timely deliverables of the work obviously is important, but at the same time, like we have to be mindful about for which industry we are, like where this research is going to be used, and who is the expert person to tell us whether the outcome or the output, whatever we are getting from the systems, what we have built, or from the research, whatever we have done, is accurate or not, or the approach, whatever considerations we have taken, whatever constraints we have thought of is like accurate or not. Also, like coming back to the other challenges, right? The skill gap, like that is the major hurdle. Like 76% of leaders have been indicating that. And we have technical hurdles also, like such as like with the existing quantum hardwares, whatever we have, right? The quantum decoherence, we have superconducting quantum computers with they have very small coherence time, right? Which we cannot much rely on. So we need more coherence with the qubits. We have the hardware limitations. We have the scalability issues. We have still limited number of qubits if we leave the annealing-based quantum computers aside. So the progress is being made, but these challenges, like whatever we have in terms of like technical capabilities of the quantum systems as well, they need ongoing research and development. So the research is going to be continued for years. We'll keep advancing the system, like whatever huge quantum systems we have, people are trying to fit that on the quantum chips, right? So how we can like bring the complexity of such big systems on a chip, all these kind of researches are happening. So the complexity of like integrating quantum and AI system sort of like is a necessity for bringing a unified hybrid platform so that we can seamlessly combine the power of quantum and classical both for the solutions for the problems what we were trying to solve. And these kind of like integrated infra will sort of like maximize the potential of this convergence and will drive the meaningful impact. So we already have like quantum computers in the cloud. We have some sort of like whatever we do on the classical computer, we designing the circuit. If you have to partition the circuit or sub-circuit simulation, if you have to do on the like quantum simulators, those can be performed, and you can measure the value before like you can run the circuit on the simulator first. That means we run on the classical first to see like what results we are getting. Then after that, like if we have optimized the circuit enough that we should be running that on the actual quantum computer, we go and run that on the actual quantum computer using the different publicly available quantum computers, whatever we have. So let's talk a bit about like future outlook and call to action. So as we look towards the future, right, the trajectory from 2025 to 2030 promises and like accelerated convergence of AI and quantum technologies. AI will increasingly be combined with other transformative trends further so that we can accelerate the progress and create new paradigms. Also, like we are anticipating a value shift in the quantum market and moving from like hardware towards software, and like how we can make the quantum solutions more accessible and adaptable. That's going to be the key focus moving forward. And this is a global race, like with like new quantum technology startups emerging worldwide. Like in India also, we are seeing a lot of startups being created and emerging, right? Particularly like I mean, some of the very promising startups which have been emerging is like QPI AI. They have built the quantum computer also for India. QNU Labs, right? So they have been like doing a lot of work for the nation, and like not just for the nation, even they are sort of like creating the impact globally as well. So QNU Lab, they have developed the whole cyber solution, which I was just seeing the video of their founder a few days back. The whole suite, they have the whole team of researchers and scientists working on such kind of solutions. So that's why that like organizational readiness is going to be the key. And currently, only 12% of the organizations are prepared to access quantum opportunities. Forget about the use cases and having the initiatives and all. Only 12% organizations in the industry are having the readiness to access like the quantum opportunities. And this is a very huge gap, which sort of like presents both a challenge and an immense opportunity also for those who can act decisively, right? So what is our call is going to be for the like call of action is going to be. So for leaders, they need to start quantum literacy programs now, invest in hybrid quantum AI infra, build interdisciplinary teams that can bridge the gap between these complex fields. For organizations, we need more pilot projects in domain-specific applications. They need to partner with the quantum ecosystem players so that they can leverage existing expertise and accelerate the adoption. And at the same time, like whatever development or adoption we are going to make in the field of quantum, we need to have a responsible AI governance frameworks also, so that we can ensure the ethical and safe deployment. So people have already started doing the research on responsible quantum, also like how we can make use of quantum technology responsibly so that it doesn't violate the ethical concerns or the safety of the human beings, right? For society, we need from society, we need support for quantum education initiatives so that we can build a future-ready workforce. We need to address the ethical implications proactively so that we can ensure this technology is going to benefit all. And also the collaboration is the key. So we need to foster international collaboration to accelerate the research and share the best practices. I understand that, each of the countries have certain IP concerns, uh, controls over technologies, imports and exports. But if between the nations there are certain uh, you can say programs which promotes the research activities across the institutes, they should be collaborating with they should be looking for the institutes should be looking for international collaborations with other experts across different countries, universities or labs, so that whatever the best practices we are adapting or we are uh, following, we can share with them, and whatever they are doing, they can share with us. And that's how the cross learning happens, right? So in conclusion, before I take you to one of the hands-on example, 2025 has been marked as an inflection point where quantum and AI convergence will become commercially viable. And healthcare and finance are going to lead the adoption with measurable return on investment. And success requires sort of like an interdisciplinary approach and proactive preparation. And organizations who will be acting now will capture first mover advantage in this exciting quantum AI era. So that's all about the theoretical aspects, like whatever I wanted to cover.
Naveshri ma'am, I request you to mute your mic.
Okay,
I request
I think they muted, ma'am. Thank you for calling it out. Yeah, if you have any questions or any thoughts, feel free to
Sir, there
unmute
is a
yourself.
question. Yeah, sir, there is a question posted. In the field of material science, any test cases they're asking, sir?
In the field of material, yeah, there are very basic example I will take. We are seeing a lot of initiatives from the government and from the private sector also on the electric vehicles, right? And how we can make sure that the electric vehicles are of good quality. They can have longer run time, longer mileage on one charge, how fast they can be charged. These are some of the key properties of the batteries which are used in these electric vehicles. So quantum computers, can be used in the discovery of new kind of battery materials, which can store the energy efficiently, which can be charged faster. That is one of the example you can think of. In the drug discovery, I'm not the I'm not the expert in the pharmaceutical industry, but I know whatever drug molecule simulation the scientists have to do in the pharmaceutical industry, it takes for them to months. It takes months for them at times, even if they run it, even if they run it on the supercomputers as well, right? So a couple of, I think one company, I don't remember the name. I can search it after this. They already have started they partnered with one of the companies and they already started sort of leveraging quantum computer for drug discovery. So let me search over here for you. Drug discovery using quantum pharmaceuticals company. So you can see 14 companies have already started using quantum theory for drug discovery. And that is the news of last year, like Academia, Algorithmic, and there will be many other companies as well. There's few big companies as well, if I can find the name. Qubit Pharmaceuticals, Polaris Quantum Biotech. D-Wave is partnering with companies like GlaxoSmithKline and Maintain AI for faster and more efficient computer-aided drug design. So these kind of use cases you will find in the material discovery, and not just these, even in the when we have to discover the material for the cars, vehicles, right? We need if we can sort of we know what properties we need in a vehicle body. They should be stronger. They should be resistant from the impact and many more properties as such that. So with the help of quantum computers, they are able to define the constants, like what properties they are looking for, and simulate the material discovery process there as well. Yep. Any other questions? Pati, Jaya ma'am? Ma'am, you have raised your hand, ma'am also. If you have any questions, you can unmute yourself and ask.
Jay Kumar sir.
Jay Kumar sir. Okay.
Jay Kumar sir, you have any questions, sir?
A company which is using quantum computers. Pharma company.
Sorry. Yeah, pharma companies. So these are the few of the companies which have been partnering with the quantum companies. Okay. So Qubit Pharmaceuticals, then D-Wave partnered with GlaxoSmithKline and Maintain AI. And by the name itself, you can see they are the pharmaceutical companies. Sometimes there are small companies which help the bigger pharmaceutical companies for the faster drug discovery processes. So that's how the collaboration is happening in the industry right now. So this is the website of Qubit Pharmaceuticals. You can just go through it. You will find all the use cases, how they're doing the molecular simulation, data advantage, and all certain stats, whatever they have been mentioning over here. So what are the areas in which, what are the target pathways they have been following, what they've been able to characterization, hit to lead to pre-candidate. What are the state of this research also you can see over here. So yep, you can see 40 plus drug discovery programs brought to preclinicals and clinical stages by DETEC team members. 30 plus PhDs, 500, they've been doing a lot more. If you follow this company, this and multiple other companies also have been focused. And this is the report which was given by McKinsey in 2021. And since then, this field has been improved or has adapted the quantum a lot, after 2021. This was the focus area and where the value lies for pharma industry in R&D. So yeah, this is what is happening in the pharmaceutical industry. Any other questions? And this is the latest this year Jan report by World Economic Forum as well. If you go through it, you'll be able to understand like what are the traditional method where quantum computing is showing its advantage in potential drug discovery. So like you can see ligand protein binding. Stats, I think they're not sure. It's just an article, but like it will be a good brief read to understand. And this is by D-Wave, like which companies they've been partnering with and what kind of use cases they've been working on. So this is one of the case study you will find on their page. Menton AI, the company which I was showing you, like COVID-19 with quantum peptide therapeutics, like that's one of the case study they have mentioned over here. And apart from this, Pfizer is one of the largest companies, right? You can see the article like published by them as well. Like how a new molecule is a potential drug candidate and how they can discover that using the quantum computers. This is the whole article regarding that. Any other questions from anyone?
So the industry-specific progress on quantum computing and its use cases in the industry platform has a different exposure altogether. And when you talk about in academia, it would be completely different. So how do you think one in academia could bridge this gap? Because that's where we are. That's a challenge, and that of course has opportunities as well. So can you just highlight what would be the best way to bridge the gap? Because their end is a high technical end where they have a lot of exposure, but then how does an academia person reach out to this and start working on that?
Agree. So the same way, like the industry people also have the gap. I will start from there first. Like being in industry, it's not easy to know like what exactly has been done in the academy or in the labs, right? So a lot of companies already have started partnering with the universities, like in US and India also. I know like a couple of companies have have tie-ups with couple of institutions. So that tie-up, that collaboration, or you can say that MOU signing is very important with between industry and institutes as much as possible. And the problem statements, whatever people, professors or PhD students or postdocs have been researching on or mentoring on, right? This problem statement, I mean, we can go ahead just with the like academia expertise as well. That's good. But if someone is interested to directly add or show value in the industry side as well, maybe try discussing with the innovation team of that company or the research team of that company and see like what problems they have been working on and try to follow sort of like a collaborative approach over there where both the team can work together, like the researchers from the institute and the research or the point of contact person from the industry as well to like finalize the problem statement, to like brainstorm on like the approach and the methodologies to evaluate the results. Such kind of collaboration will make sure that whatever research is happening also like is getting used also at that, because a lot of time like I've seen people do write the research papers, they publish it, they will have their name on the research papers. It's a very good thing that act as a base, but a lot of research work gets, I mean, like people are not seeing it much, right? Like if apart from the academia people, how many people are actually reading the research paper? So rather than just like isolating the research work, if we collaborate with the companies, if we collaborate with the like let's say if you're working on some healthcare problem, whatever local hospital also you have in your city, you speak with the doctors. Okay, this is the model I'm working, I need this data, can you provide to me? Start from there, include their name also, because they are also going to be the like active like contributor
Correct.
to your project, right? Then test also the models along with them to see the efficiency of that model, like how much we can rely. Based on that, take their feedback, iterate the research work again and continue that process.
Okay. Thank you. Thank you for that clarification.
Thank you, ma'am. Any other questions from anyone? Okay, if not, I will just quickly talk more about a few more companies. So Continuum, I don't know how many of you know this company, but they have been actively working on the quantum and AI side. And one of the famous scientists, his name I'm forgetting, Bob or something, whatever the name is. They have been working on QNLP side as well. So they have different libraries which you can explore and try to look at like what the roadmap is, what kind of problems they have been solving. So their key focus, if you see, have been on the computational chemistry, that is material discovery, molecule simulations, drug discovery, and all. Quantum hardware, they are using the quantum computers powered by Honeywell. Cybersecurity also, like they are providing the quantum random number generators. They have the whole stack, and so this is one of the company which have been working on QNLP as well. So if any one of you are just sort of like sorry, what did it open? If any one of you are focused on like how quantum can be applied with like large textual data set, this is what you can go through. They have a library also like released. They have some sort of like documentation and programs as well, which you can follow. So this can be like one starting point, like how we can design an implementation like NLP models. We can implement NLP models by exploiting like quantum properties. So this is on the Continuum side, and in India there are companies like Qunu Labs. Follow them, like they have Urvashi Sinha ma'am. I think she's the scientific advisor or scientist over there working with them. They have built the whole cyber suit, something I don't know the exact name what they are calling that is, but they have been actively contributing globally, like across different places. They have these products like quantum key distribution, quantum random number generator, post-quantum cryptography, and all. These three industries they have been focusing on, and they have this QVerse and QConnect platform as well. Next company was QPI AI. They built the India's first quantum computer, and they have been focused on across different industries. So if any one of you are interested in doing some research, you can reach out to people from QPI, Qunu Labs, see what their key focus is. You can jointly like agree on some research statement and can start the work. And like these companies also fund the research as well. Like if you're doing it, it need not to be like without funds. So whatever as an immediate research work, whatever they're looking for, they can be like it can be done in partnership with them. So they built a 125 qubit quantum system in India, and they have the whole roadmap of like scaling the system to higher number of qubits. Okay, this is one company. Then there's another company I want to talk about, Quantum AI. Okay, this company was founded by Sanjay Chitori, so like Quantum AI Global, and they are also doing good. And they have built products also like I think they were working on Quantum RAM. That was the one product which I heard of, and there are like other areas also they have been focused and working on. So these are the services. Let me see like if they have mentioned about their products clearly somewhere. Yep, these are the like their product ecosystem: QFolio Pro, QMemory, QMag, CheckQ. You can see right there's a whole suite of like quantum tools which they have been preparing and they're doing. So obviously to improve these products, to make sure that we are sort of like adapting to the latest research, whatever is happening in the industry, they need researchers and people from the academia. So quantum AI is one thing. And then we have one more very innovative startup from India, QKD Satellite startup in India. And like I was amazed when I like heard about them, like how they are how ambitious they have been in exchanging or sharing the or distributing the quantum keys through the satellite. So what was the startup name? Yeah, Space TS and Synergy Quantum. They have collaborated to develop indigenous quantum secure satellite systems. So such kind of startups are like also emerging, and they're making change like globally. So these are some of the areas if you want to get started with. If since I talked about quantum machine learning here today, right? So few resources I wanted to share before I end today. This is tough. Not this page. Yep. So if you come to the IBM quantum ecosystem, for example, this whole like Qiskit machine learning documentation page, which you can open and you will find a lot of tutorials to get started with. So if you just start with the basics, quantum neural networks algorithm, it is very well explained. Obviously, there are certain prerequisites. If you don't know the basics of quantum, if you don't know how to code in Qiskit, then that will be a challenge. So first cover up those basics and then start with these kind of notebooks as well. This will give you the like better understanding of how you can load the classical data, how you can encode that to the like quantum format, quantum data, like using some data encoding techniques. Once you have the data encoded over here, then how the data processing like happens in the quantum circuit. Quantum circuit is called as like ansatz over here. Then measure the value and get the outcome like what we're trying to get. So such kind of examples, links, code, everything you'll find over in this kind of pages tutorials. So this quantum ecosystem is the page which you should be like knowing of. Using PyTorch, if you want to implement like hybrid classical quantum neural networks, you can use Torch Quantum Library. We have Qiskit Finance for finance use case. We have Qiskit Optimization for like if you are trying to solve any optimization problem. We have like Air. This is the simulator. Like if you want to run anything first on the simulator, you should use Qiskit Air first. Like that, the different libraries like Qiskit Algorithm and Qiskit Dynamics for like creating dynamic circuits and all. Qiskit quantum error correction algorithms. So a lot of like resources you will find on this page itself. If you just start with it, that will be like really great. And also at the same time, like try to collaborate with international quantum bodies as well. So see how you can become or organize parts or deliver lectures for Q World. So we have Q India chapter as well. So this is a like non-profit organization. They have chapters across different countries. Many of you would be already knowing about them. So try to like build communities within the colleges of within the college first. You can start from there and scale that at a national level or global level as well by hosting some sort of like monthly events and so, right? And then other one is like Open Quantum Institute. So Open Quantum Institute is also like this non-profit organization got spinned off from the CERN, and they have been doing a lot of work for multilateral governance, diplomatic dialogues, initiatives on quantum technologies, helping developing nations in organizing hackathons. All these activities are happening. So try to like look at their page also, go to the get involved and see how you can become part of such communities, how you can contribute at the international level by like in like collaboration with some of the global scientists. Urvashi Sinha, ma'am, like she knows about all this firm, like she's already part of Chesta and all. You all like can also be part of it, like if you're interested over here. So I think that's it from my side. If any questions, I will take that up before I end up. If anyone wants to reach out to me, feel free to reach out to me on here. So this is my LinkedIn QR. Like if you just scan it, you will you can like connect with me, or on LinkedIn you will find my username as like Tech with Shadab. Feel free to send the request if you have to discuss or have some ideas to like collaborate on AI projects or quantum projects. Like I'm open to discussion. So yeah, that's it from my side. I will stop sharing the screen. Any questions from
I
anyone?
request if they have any questions, they can ask. Now, since the sir is open to questions, if you do have any questions, you are open to ask.
Sir,
Okay.
this is Pratap.
Thank you, participant.
Yes.
Sir, this is Pratap. Actually, could you able to share this all the sites, whatever you told in the last project's possibility, no? Is there any possibility could you able to share in the form of one notepad or some all the sites alone, just sites alone?
Sure, sir. I can try sharing. I will share with Prabha ma'am. Maybe she will sort of like.
Sure, sir. Sure, sir. That is sufficient. That is sufficient. Just last 10 minutes, whatever you showed the project's possibility of the project of collaboration with the international or whatever. If possible,
Yes.
if could you copy all the sites in one notepad or the wordpad, and if you could able to share, no, that will be great useful for us.
Sure,
Thank
Pratap. I will do that. I will share with ma'am, and she will forward it to you. If you don't get in like 2-3 days, you can ping me on LinkedIn.
Sure, sure, sure. That's obvious. Thank you. Thank you so much for that kind words.
Thank you, sir. Any other questions from anyone?
I think we are done with the question and answers, sir. On behalf of Ramaya University of Applied Sciences, I thank you, Shatabh sir, for sharing your knowledge and time with us and telling us the importance of collaboration towards the research and to build the industry gap towards working towards the convergence of quantum computing and AI. It was very useful, and thanks for your time, sir. Thank you.
Thanks a lot, Anita ma'am and Prabha ma'am for inviting, and it was really nice interacting with you all. Thanks everyone for attending the session. Have a good
Thank you
rest
so
of the
much, sir.
evening. Yep.
Thank
Thank
you.
you.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Participants, kindly fill the feedback form.
Ma'am, will the PPT and the other things be shared with us?
Once we get all the materials, I will share you, ma'am.
Sure, sure. Thank you so much, ma'am.
Actually, they've given the previous PPTs they have given. Still, it has to be updated. So, updated PPT, once I receive, I will send you everything.
Sure, sure, ma'am. Thank you.
Yeah.
Ma'am, my message box is not enabled, ma'am. So feedback form link. I got it through WhatsApp, ma'am. I got it through WhatsApp.
Yeah, thank you, participants, for your patience listening. We shall see in the tomorrow's session. Thank you all.